Hello, everyone. Welcome back to the AAS YouTube channel, and this is part of the good stuff. This is the AAS Journal Author Series, and I'm very happy to have Navin Chandra Joshi with us today. Hi, Navin.
Hi, Frank. How are you?
I'm doing very well in my morning. Where are you located?
Okay, fine. I'm in New Delhi, that is the capital of India, and it's the near the Delhi. It's called NCR region, near Central Capital Delhi region. And right now I'm in my campus. It's my room. That's all. So yeah, it's
Very
all
good.
about yes.
Very good. So yeah, we are basically really are on opposite sides of the earth here as we give it a chat.
Yes.
Let's see, it's coming, we went past equinox, so we're coming into the winter months in India. What are some of the changes that take place in India as you transition into winter?
Okay, fine. So actually, this is starting of it is the month of October here, and today we have a big festival in India. It's called the Dashera.
Cool.
It's a big festival. Okay, so in that day we celebrate the victory of Lord Rama. That is a very famous Lord in India. So today is a national holiday as well. People are celebrating like the big festival, and we are here. So after that, when the October is going to be end, we have winter started. Yeah, so it's this time of cool, warm winter is like this, not that much warm. That is not that much cold. But as soon as we will enter into November and December, it is in Delhi region is going to be very cool. Sometimes we feel 0 degrees, not zero, but 5 degrees, 4 degrees, around that. So that says we are entering into the winter. Now it's okay, but the future or the upcoming 2 months will be very cold as far as this region is concerned.
Cool. So I'm here in Phoenix, Arizona in the US, and today we're getting a cold front moving in. So it will drop a good 10, 15 C today and be a little bit on the cooler side today in Phoenix. So that'll be fun.
Okay. Fine.
So Navin, what do you like to do for research?
Okay, so my field of research is the study of sun and their activity phenomena. So whenever we see the sun, actually, if a normal guy see the sun, he say that just it's a hot object. But from the observer eye or from the researcher eye, if you see the sun, so there are many things happening in the sun, in the time scale from minutes to the hours, right? So my work is basically the eruptive phenomena that occurs on the sun. These are called like solar flares, eruptive prominences, filaments, and when these eruptions enters into the solar corona, that is the outermost layer of the sun. So that is we'll call them coronal mass ejections, that CMEs in short. So my work is to find out what is the actual triggering processes that behind these eruptions, what caused that eruptions and what triggered these eruptions. So sometimes these eruptions are too huge and big, and if these eruptions are erupting towards the Earth in the Sun-Earth line, so they can interact with our Earth's magnetosphere as well. So in that way, it's very important to study the Earth-directed eruptions in the point of view, in the point of view of the space weather research. That because in between the Sun and Earth, we have many things like spacecrafts and telescopes and observatories and all the space observatories and everything. So in those terms, it's also important to find out what's the triggering process, when it will be triggered, and this area is very practical applications as well. So that is my field of view of research as of now. Yes.
Cool, very nice. And that is going to lead us into this very lovely article on sequential lid removal in a triple decker. chain of CME producing solar eruptions. Navin, take us away.
Okay, fine. Thank you, Frank. Uh, let me let me tell you guys something about the article that I have, or not, we have published in the recent a few months ago. It was published online. So I have with my collaborators, the Stalin and Professor Moon, Professor Stalin and Dr. Joshi. All these are my co-authors here, and two of them are from NASA GSF, MSFC, and one guy is the Bhuvan Joshi is from the Udaipur Solar Observatory. That is a solar observatory is situated in the Udaipur city in the Rajasthan province of India. Okay, so that is all about, and that is the first author is myself. And actually, when we were looking for some eruptive events, so we found this very interesting event that occurs somewhere on we will discuss later on when we'll see the paper. So in that paper, what our aim is to find out the cause or the triggering process of the triple decker chain of CME-producing eruption. Actually, we found three consecutive eruptions from the same region on the sun.
Okay.
Okay, so that is called that's why we are calling the chain of CME-producing CME eruptions, and the triple decker that I will going to discuss in the later when we'll discuss the paper. Okay. So in that way, okay. So can we move ahead? So that's why. Okay, fine. So in that way, let's we can move to the first figure, and then I will explain what was the reason on the sun that we are observing, especially for this paper. Okay, so here is the first figure. Fine. So in that figure, you can see that is the eastern or the western part of the sun, half part of the sun. Especially in the terms of solar physics, we call this part as a western part because we are looking for the sun. So in that case, the box is showing some number AR number 11745. Actually, in the this is called active region because in the sun you can see there are some quiet regions where nothing is happening. That is that region. But there are some other regions where there's some brightness we can see in the AIA 1304 angstrom. Actually, let me introduce this SDO AIA. This is a spacecraft. It was launched by NASA long ago, and it is called Solar Dynamics Observatory. And in that the set of instrument, there is one instrument is there in that space observatory, that is AIA, astronomical astronomical AIA. AIA is name of the that instruments, and it is that image that we are here is 304 angstrom. That is the extreme ultraviolet image of the sun. We have various wavelength, and in the properties of the sun like this, if you observe the sun in different wavelengths, so we can see different features. That's the very unique thing is that you can compare here. So that is the SDO AIA 171 angstrom image is there, and here you can see some loop-like structure. The structure that is coming in that way and that way. These are actually nothing but the magnetic field lines of the sun. Yes. Okay. So whenever, yeah. So the active region, which we are showing here in the box, is representing the zoom part of that box is representing here. So you can see that is the region from where we have observed the three consecutive eruptions one after another. So that's why our aim is to find out what is the cause of these successive eruptions, because people are working on this field and they are working on a single eruptions or sometimes double eruptions, but sometimes from the same active region is we have consecutive eruptions. So it's interesting to find out what is the cause or the triggering behind these eruptions. Fine. So if we go slightly lower, there's one more figure. Yes. That is the different wavelength. Okay, can we go up like slightly up? Okay, so
Which one?
yes, okay,
What do you want
okay.
something?
Yeah, that's fine. So in the first figure, we have see that where the active region was there, and actually in the sun, if this any event is occurring, so we have to first focus on that part from where the eruption or any event or any sort of activities are happening, and then we have to focus only that part. So that is the localized study of the sun, not the global one. So here in this figure, this is the magnetogram.
Mhm.
Okay, in magnetogram images of the sun. It is showing the magnetic field polarity. Actually, this is the photospheric image because if you see the sun, so start from the photosphere, and then the next layer is called the chromosphere. Then the outermost layer is called the solar corona. So that's the atmosphere of the sun. So actually, this is the magnetogram, and it is another instrument HMI. It is onboard SDO, so which is observe the magnetogram of the sun, and the wavelength that the HMI use is 6173 angstrom. Okay, so in that picture, the positive reason that we have, it is the positive polarity reasons, and negative dark color or black color is representing the negative polarity region. So actually, if we consider it as a bar magnetic, like a magnetic field, so field line will start from the positive region, like a loop, and they end in the negative side.
Yep.
Okay, so that is the magnetogram. Actually, we are showing the sequence how the magnetic field is changing. Actual event is occurred on 22nd of May. Okay, but we are observing the magnetogram from 18th, and then 20th, and then 22nd of May. So it is a sequence of magnetogram. We are studying for 18, 19, 20, 21, how it is changing. So if you see there is no big change we can see in the magnetogram, it's the structure is almost is like same. We have is the positive polarity on the left side and the negative is there. Overall, it is moving in the same way. There is,
Yep.
however, there will be some small changes will be there, but that's fine. So the overall magnetic field is like same. It's bipolar kind of active region. So the field line is starting from here, and this is the circular dark region here in the center in that image is called the sunspot. Okay, so that region is called the sunspot. Fine. So this is the photospheric magnetogram on what is happening in the photospheric region or the layer of the sun. So if we go slightly down, if we go slightly, yeah, in that figure. So here, what we have did, we have actually plotted. See, so dark white regions is called the positive polarity regions, and the dark region is called the negative. However, the background resolution is not that much good, but still you can see that this is white region, this is black region.
Right.
Field line actually starting from here and going like this. So for these kind of measurements, we have to depend on the some numerical techniques because we don't have the direct measurement of coronal magnetic field at this moment. So we have to depend on some some techniques, numerical techniques. So here these are the PFSS technique. It is called potential field source surface uh, analysis. If we run that code, it is actually a code, and this is the theoretical code. And when we will give the boundary condition of the photosphere from the background, from the actual HMI image, it will plot the magnetic field using the coronal magnetic field condition, something like this.
Okay.
So these are the techniques we have. Okay, so the active region is like bipolar. Mostly left side is positive and right side is negative. So field lines is going like this. Some field line is very long, or this is called overlaying coronal loops. Okay, and some is very low laying. It's called low laying coronal loops. So that is the overall configuration of the active region from where the eruptions is going on. That's all. Okay, now we will move to the next figure. Okay, and next figure will show how it happens. So in between we have all the Okay, now let's discuss something about this figure.
Okay.
What is this? That figure is the time temporal evolution of flux. What is the flux? Soft X-ray flux. Okay, so its unit is watt per meter square, and we have a spacecraft. It's called GOES, GOES, geocentric operational. GOES is short form, is GOES. So that's spacecraft actually giving us the integrated flux of the sun. Integrated means it is taking the whole sun as a one object, and it gives us the magnetic flux. So the black curve is the flux in X-rays, okay, in different wavelengths, 0.5 to 4 angstrom and 1.0 to 8 angstrom. So we have two band, different filters, and then corresponding to these, we have two like curves. Okay, fine. And these colorful graphs, there are some colorful graphs also there, and these colorful graphs are from different spacecraft. We have a spacecraft which is called RASI, and RASI spacecraft is observing the sun in different energy channels from soft X-ray as well as in the hard X-ray.
Okay.
Okay, that's okay. So overall, we can see three peaks or three bumps in the flux measurements. So one bump is here, second bump is here, and third bump is here, or that is actually here. Okay, so these three bumps are actually associated with the three eruptions that we have observed from the active region that we have discussed earlier. Okay,
Okay.
so now that is the temporal evolution part, and then in the next phase or next figure we will see what will happen observationally at this time, at this time, and at this time, and then finally we will interpret it using the one technique or the one model that we have given for the triggering. Fine. Can we okay, if we'll go slightly down, yes, we have another plot, uh, this one, but is this the more or less the same for the first, second, and third bumps. Actually, these bumps in the soft X-ray is called solar flares, and we have three flares associated with the three eruptions, as the soft X-ray is showing three bumps. Right. And the red curve here is the intensity plot. Intensity plot is, we will take the, it is AIA 94 angstrom image curve. So what we will do, we will take the 94 angstrom data, and for those particular region of the sun from where the eruption is occurring, we will count the intensity of each image. Actually, we will get the AIA gives us the cadence of 12-second cadence of the images. In each 12 seconds, we'll get the image of the sun,
Okay.
and then we will count the intensity of each image in each 12 seconds, and then we will plot it. So it is matching with the soft X-ray. So what it will show that the most of the soft X-ray, because the background soft X-ray is a full sun's, it's an integrated X-ray flux, not the that localized regions flux. But this AIA 94 is by which we have estimated it is a localized region intensity flux of AIA 94 images. So if we're comparing it, it is matching. So we can say the integrated flux of the soft X-ray is the most of the X-rays coming from the same active region at the these timing or at the these time. Okay, because at the same time two events may occur. One is in that portion of the sun, one is on the northern side, one is on the southern hemisphere, one on the eastern hemisphere. So sometimes if at the same time 2-3 events are occurring, then it's difficult to distinguish between them.
Okay.
So for this kind of analysis is important. Okay, fine. So that is about the intensity mappings. Now, if we'll go to the next few slides, next figure, then and the next figure, yes. Actually, when this is the three images of associated with the first eruption. Okay, so first eruption started around 2:30 UT. You can see here a dark channel-like structure And these dark channel-like structure is called active filaments or the filaments. It is active because now it is slightly moving upward or the away from the solar surface. So whenever this kind of structure is going upward, it is called active filament. It is now active. Okay. And here at the same time, maybe around a few minutes later, we see yes. So we are here. Here what we can see is some part is developing and growing outward, and in that way this is the hottest channel because each AIA 335 angstrom and 131 and 94 angstrom channels, this is the hottest channel, means the emission that is coming from the hottest plasma, because sun is in the plasma state. Here it is the mixed plasma, it both contain hot and cool, and here it is also some mixed plasma. So we can see some development of flare arcades here, like this one. And in that way it is so the overall what is happening here is the eruption, some activation of the filaments, and soon the development of overall arcade, overlaying arcade, and the development of flare arcade. So it means something is going on, and then we have a formation of flare arcade at the very low laying region of the sun. And these, if we'll go slightly if we'll go slightly downward, we can see yeah. So that is in the next figure, I think we can see some more interesting feature related to this first eruption. Okay, fine. Now, very interestingly, you can see these are the stereo A EUVI 194 angstrom image. Again, the different channel, and we have different spacecraft, different space observatory. This is stereo A. Okay, and you can see now we are observing the east limb of the sun, and this east limb is why? Because the AIA is observing on the west part of the sun, and through stereo A, because it is located at the different projection. So it is AIA and stereo A is able to observe the western part. Okay, because one is on the front and what is on the slightly front. So we have two spacecraft which are observing the sun from the two different angles. So we have multi-angle point of view. For the AIA, it is on the eastern side. On the stereo A, it is on the western side. So it is multi-angle observation. So sometimes these kind of observations are very important to see the same eruption from the different point of view, this different angles. So here the same eruption is there, but from the eastern side. But it's the same eruption. But because of the spacecraft is located in some other position, so we are observing like this. So we can see some erupting loops that is like going like this way and this way and this way. And this is the difference image. What we will do, we will difference two images. Here we are two images at 230 and 225, and there we are subtracting two images. So we'll get these kind of images. This kind of is good for see the fine structure. These eruptions we can't see in the AIA observation because of some because of some resolution effect on and what is the pixel size and all these things. Here we can see clearly. If you go slightly downward, we can see the structure of what is going on there in the lower solar atmosphere. Yes, fine. Yeah, here if you'll see in the AIA 304 angstrom image, some low laying brightness we will observe. Okay, usually these kind of brightenings we observe, and in the AIA 304 angstrom, and these are called the flare ribbons. Flare ribbons are forms in the very low in solar atmosphere, and the flare loops are connecting from these brightening regions. So R1A is the left side ribbon, and R1B is the right side ribbon. And these are R0A and R0B. These are the very innermost flare ribbons that we have formed. Okay, yes. So in the magnetogram, we can compare their location. One is on the positive polarity side, and second is on the negative. This is AIA 1600 angstrom image, and again we can see some long bright structures. These are very well compared with the AIA 304. So these are the flare ribbon that we have for sure. So first eruption, because whenever there is an eruption, so eruption is going on, and then there is a reconnection at the beneath the eruption, and then we have the formation of flare ribbons. So that is the overall scenario of the flare ribbon we have. Okay, we'll discuss more in the last when I have drawn the schematic of this representation. But till then, we will see the observation. If we'll go to the next figure, we will see what happens with the second eruption. Okay, so in that case, from the same active region. Okay, here quickly I will discuss about this figure. Here in this figure, this is stereo A EUVI height versus time plot. Okay, it is a height time plot of the first eruption that we can do. What we will do, we will take the leading edge of the eruption from the images and then calculate its height from some common reference point. These are these heights, how the height is changing here and with the time. And then we will fit a linear fit. And as we know, if we'll get the slope of this curve, we'll get the speed. That distance divided by time will get a speed. That method we will use. This is for the first eruption. Okay, and these are for the second and third eruption, but we will discuss it later on. So it is the same technique we have used for the second eruption and the third eruption as well, and we have shown here on the same figure. Okay, the speed is around 167 for the first eruption, 43 for the second, and like average is around 13 kilometer per second, the slow speed for the third one. Okay, so this is about the height time measurements of the eruptions. Fine. Okay, if we'll go slightly in the next figure, we will see how the yes. So that is for first, this is for second, and C this is for the third eruption. Height time measurement. Now we will go to see what happened with the second. Yes. Here, these are the sequence of images of SDO AIA 94 angstrom images from 725 to 810. So we have shown the three figures. Dotted curve is showing the part that is going to be erupt. Yeah, the dotted, very faint dotted lines. These ones. So these dotted lines are going to be erupt. You can see how this line is along which this is a trajectory along which the height time measurement have been calculated. So this is all about the second eruption, and here the formation of flare arcade again, because every eruption, not every but most of the eruptions are associated with the flare arcade beneath it, and is usually connect the positive polarity to negative. And the reconnection of the flare reconnection occurs somewhere at the top of the arcades and the eruption. Fine. If we'll go slightly downward, we will see the different angle. That is the stereo images. Again, as I've told you earlier, it is a different angle. Okay, it is the eastern limb. And nicely, is the difference images, we can see the huge loop-like structure, which are like connecting like this way, and it is moving up. So it's again the difference images with a different angle, we'll see the same observation nicely. Okay, so that is about the second eruption from the same activity.
Yep.
Okay, fine. So if we will go to the next figure, maybe we'll see what is happening in the lower solar atmosphere. Okay. Yes, let's see. Yes. Again, as I told you earlier, that we have, whenever there is an eruption, it shows some ribbon-like activities in the very low solar atmosphere, not in the corona, but in the chromospheric region. You can see the second eruption is also associated with the two ribbon-like structure that is called R2A and R2B. Okay, and here again, this is AIA 1600 angstrom image. This is more lower atmospheric region than this one. This is chromospheric, and this is transit region, more lower than this. And this is stereo A image of the different angle. So that's why the ribbons are on different projections. But this shows that we have again the ribbon-like activity associated with the second eruption. Fine. Now, if we'll go slightly downward, we will see the loops that are connecting these ribbons. We'll go slightly downward in the second part, that is figure D, E, and F. Here, you can see some loops or some arcades connecting from the two long ribbon like the ribbons. Yeah, here. This is AIA 171 angstrom. All these wavelength channels are the extreme ultraviolet wavelength channels. Fine. And here it is a stereo A of the different projection, but again we can see some loop-like structure that usually these arcades will form after the eruptions, and after the eruption reconnection occurs, and then the particles channels down in the lower solar atmosphere, they hit the lower part of the solar atmosphere and then brighten up. So ribbon will form, and then these are the flare arcade that will form after the flare reconnection. Okay, so that is about the second. Let's, if we'll move slightly downward, then we can see how what happened with the third eruption. Okay, and here, yes, again. So let me tell you, these arcades are formed after the second eruption. So that is the pre-existing flare 2 arcades that is already there, and like again, some eruptions from the bottom side is going to be erupt. It's the compact brightening, and then something is going to erupt from the bottom that is actually the part of the filament that is remained there, and it's erupted later on. So it is going to erupting here, and again you can see this is the erupting structure is going on, and this is the flare arcade. This flare arcade is also observed to moving on the north side as the eruption is going on. So this flux rope is pushing the arcades slightly towards the north or the northern side, and finally it is going to be erupt. So that is the third eruption, and that is actually the eruption of the filament, a dark filament that is laying in the low laying height, and later on is going to be erupt. Okay, so that is happening in the third. So it disturbing the flare arcade that is already formed during the second eruption. So that is about the second. If we'll go slightly downward, but we will observe the sequence in the panel D, E, and F. So in the panel D, we can see the deflection of loops towards the north very fast. Okay, so this loop deflection is due to the eruption, and when something is erupting on the upward side, it is pushing the already existing overlaying loop towards the north. In the same way, because as I told you, whenever there is eruption, there is a reconnection and the formation of flare arcade. So the arcade that is going to form in the very low laying is the arcade associated with the third eruption, and these loop structure is now gone or not visible because of maybe it's the temperature has been changed, or it is going to already erupted. Here we have some contours. Okay, so these contours are different color contours over this image is showing the different contours of 3 to 6, yellow color 6 to 12 keV of different energy contours are there, and green contours are 12 to 25 kilo electron volt, and 25 to 50 is like blue. So at the top we have the contours of green and red, and the blue and green we have at the bottom. So actually it's the two lobes which are very low laying is located at the flare ribbon, and the lobe that is at the top, it is the loop top X-ray sources. Actually it's called loop top X-ray sources, and these are from the ribbons. Again, in the F panel, we can see nicely in the difference image some structure like this. This is nothing but the erupting flux rope that we are observed in the AIA image as well. Okay, but it's a different projection. So this is the eastern limb, and for the AIA is the western. So we have three eruptions, one after another. If we go in the next figure, that is the figure 10, we will see some more interesting things. Okay, and we will try to. Okay, again we will see what is happening in the lower solar atmosphere.
Okay.
Nicely, again we can see two long elongated structure. It is we named is R31, and what is on the other side it is R3b. In the AIS 16, which is the more lower solar atmosphere, the same long structures are observed. It is the brightenings, long brightenings, and this is the limb of the sun. So there is projection effect as well, but still we can see it.
Right.
Here it is also very nice elongated, long ribbon-like structure have been seen, because the third eruption is the very big eruption among all these. So we have the long ribbons corresponding to that. Okay, so we have again the ribbon-like activity associated with the third eruptions. If we'll go slightly downward in the D, E, and F panel, we will see the flare arcade or the post arcade that will form after the flare. You can see the arcade structure that is going to be connect from the left to right. Yeah, it is going to be like this way. Here it is more plasma is there, so we can't see clearly, but in the 171 angstrom, which is slightly higher in temperature compared to 301, we can see nice bundle of loops connecting the long structure to the other side. Again, this is the 195, because it's 171, it is 195, they are almost at the same temperature. So we can again see the long structure, and they are the set of bundles of flare arcades starting from bottom to top. So it's long flare arcade structures are there. Okay, fine. So our third eruption is also associated with some sort of flare ribbon-like activity, as well as the flare arcades have been formed. So now if we move to the figure 11, in the continuation, we will see that how the CME. Okay, now that is the part, that is interesting part. Okay, so that is first panel A, B, and C is showing the CME. As I told you earlier, that the CME is coronal mass ejection. So what we will do actually, we will occult the sun. We have sun. If we will block the sun, and whatever is coming out from the sun, we will observe only that part. That is called coronographic observations. So here we are blocking the sun, okay, up to this part, and then this whatever is coming out is called the CME. It is associated with first eruption, because first eruption occurred from 225 to 350. Okay, so we have different coronographs. Okay, we have core 1, which is on the stereo A, and we have LASCO coronagraph, which is on the SOHO spacecraft. So we are using the coronographic field of view of two different instruments or the observatories, and try to analyze what is coming out. Sometimes the eruption is very faint, you can't see them. These are the difference images. Again, this is also a difference images. We are subtracting the one image to the previous image, and we'll get this one. Here, some faint structure is coming out that we are claiming as CME1, and here it is also some part is coming out that is also we are claiming it is a CME1, or the material that is coming out along the magnetic field, we'll call it CME. If we'll go to the panel D, E, and F, that is the panel, next panel is associated with the second eruption. Here we can see nicely the eruption that is coming out. So again, we have to occult the sun, we have blocked the sun, and now this part is coming out. So that the eruption, the structure that is moving out that we have seen in the still images, here we can see nicely in the core 1 images and the LASCO images and LASCO. In LASCO also we have two coronographs. and the field of view is quite different. You can see here the field of view is only from the 1.5 to 3, so around the solar radius. And here it is a larger field of view. You can see the sun is very small, and from here to here is very large. So the same structure is there, but is in the larger field of view. So you can see sometimes the CME has a three-part structure, that this is the filament or the flux rope that is coming out from the bottom of the solar surface. And when it is coming out, they will produce a kind of shock front that is called leading edge. And then there is a gap when we don't have any magnetic field, so it is coming dark. We don't have any density because these are the, and then this structure is called the filamentary structure, that is actually that we have observed erupting from the sun in the AIA still images. Okay, so one part, second part, and third part. It is called the three-part structure of the coronal mass ejection: leading edge, cavity, and the core. Core is usually the filamentary. Okay. In the C3 field of view, which is a larger field of view, we again see the same structure. Same structure is propagating outward, and this is the sun. And eruption is propagating outward in the interplanetary space. Okay, so the CME, along with the magnetic field, it is just not the plasma. The magnetic field is also expelling out from the sun, okay, along with the plasma. If you'll go to the panel G, H, and I in the bottom panel, that is the CME we'll see associated with the third eruption. Okay, so let's see how it looks like. Yeah, it's very interestingly or very good. Here, this is the CME third, or the leading edge of the CME third. Here is the very smallest field of view, very close field of view to the sun. LASCO C2 images is showing some complicated structure. We have a leading edge, and we can see the filamentary structure here quite well, but it's mixed. It merged with the leading edge. Actually, sometimes in the observation limitation, we can't see clearly the two distinguished structure. But here, you can see at the later time, this part, which is at the front, is the CME2, leading edge of the CME2, and the part that is coming out is the lead CME3. So it is successively going on, one after another. The CME3, then CME2, and then we have a core part structure. Here we can see some filament that is on the core part, located at the core part of the CM. So all these three eruptions are associated with the coronal mass ejection. Okay, so means it is not the failed eruptions. Okay, so there are two kind of active eruptions are there, and the first is when the eruption that is associated with the sort of coronal mass ejection, that is called the full eruption. And suppose if the same eruption is coming out, but due to some restriction, not going away from the sun, it is somehow confined there, so it's called confined or the failed eruptions. So, but in our case, all the three eruptions are the complete full eruptions. So that is the conclusion of these CME analysis. Cool. Fine. If you go slightly in the last figure, I think hopefully it will be the last figure. Fine. So through this figure, we have finally concluded or tried to interpret the erupting scenario using a schematic diagram. Okay, so lid, we know we have a kind of lid, and lid is like but here the lid are the magnetic field lines or the magnetic flux. Okay, so what we are proposing here is we have three flux ropes, one over another. See a flux rope 1, flux rope 2, one flux rope 3. These kind of structure we are showing a triple decker. Triple decker means we have a buses like double decker and triple decker. So similar, like we have a structure 1, 2, and 3. So we are proposing that initial structure would be something like this. Okay. That's if we are considering that, then we can explain the three successive eruptions from the same activity. So initially, what is happening, there is some activity here with the flux rope 2, which is at the middle one, and due to some activation, this CME2 is slightly moves upward, and if it is moved upward, it pushes the overlaying field to disturb the overlaying field, and it allowed the eruption of the blue, that is the overmost topmost field lines. So the topmost field line is going to erupt, and some field line with the flux rope is going to erupt, and there is a reconnection here, because when any filament or the flux rope is going to erupt, the outer field lines is compressed like this way,
Right.
and they're going to interact at this point where CME first flare reconnected is this point. But the second filament or the flux rope that is initially erupted, it is a confined one. It doesn't erupt. What we are going to erupt, we only see the eruption of overlaying field line. Okay, so that is the scenario with the first. Okay, and it removes some of the lid, the first lid or the overlaying field line from. Okay, so actually eruption is based on the overlaying field line. More the overlaying flux we have, the filament cannot go out. Okay, so we were this here. This is the sort of mechanism we are giving for the eruption of first eruption and the association of first CME. Okay, now if we'll move slightly in the panel C and D, uh, we can see the second lid is associated with that some red lines and some blue lines. And now what is happening? The flux rope 2 is going to destabilize and try and going to erupt in the later phase of the activity. So when this flux rope is going to erupt, again the field line which is surrounded the flux rope is going to be reconnect at the bottom or the beneath it, with showing by the star red color, and it is moving up, and along with it, it is taking away some of the field lines, the blue field line with them. So again, the lid that is covering some part of the blue field line and some part of the red field lines over the filament 3 is going to be removed. Okay, and now if you see that the CME is going up, and now we have only the third CME is the third flux rope is there. And the third CME, third flux rope, is now finally erupted, and we have reconnection again at the red star, and we have the flare ribbons showing by R3A and R3B. You can compare this schematic with the observations, and it is finally going to be erupt, because now we do have very less flux over the flux rope 3, and now it is facilitate the eruption of third CME is very fine. So now finally the third flux rope is going to be erupt. So in that way we are giving a sequential lid removal, a mechanism for the eruption of successive eruption of flux rope one over another in a triple decker flux rope like structure. So the schematic that we are showing here is based on the careful inspection of observations and their detailed analysis. After that, we have made this kind of schematic and gave the lid removal mechanism for the successive eruption of 3 flux rope. Okay, so that is still the mechanism that we are discussing. The lid removal is not going to be studied very much, and the Professor Starling and Moore give this idea in 2014 with some of their events, and now in that with the help of this paper or with this event, we are trying to means explain the phenomena in the more detailed way. In the future, more analysis of the same kind of events is possible to explain better the eruption of successive flux ropes and the CMEs. Okay, thank you very much.
Thank you very much. So it looks like
Yeah.
the future is bright. We're going to have some more of these, and we'll be able to study them in a little bit more detail observationally and theoretically.
Yeah, yeah. Actually, yes, we need actually, because in the from the same active region, if the three successive eruptions are going on, then what's the mechanism for that?
Yeah.
If the eruption is from the different active region, then that's fine. But from the same active region, how the overlying magnetic field is changing and how it is facilitating the eruption of the underlying flux. So that's the important things that we have addressed in that paper, and in the future, more studies are needed. Yeah, sure.
How common are triple CMEs? Are they rare? Are they fairly common?
Okay, actually, the successive eruptions have been observed on the sun. It is not like it's uh, very common, but the successive eruptions we have observed in the sun. But from the same active region, it take time. I mean, like there are intervals. Suppose the 4 hours in 4 hour interval, 5 hour interval, that kind of event have been observed before, and sometimes they have observed the two nearby active regions. One is erupting from the one active region, second is erupting from the nearby active region. This kind of eruption is also called sympathetic eruptions that has some relation with one another. But from the same active region, there are some papers, but still we need to work on that, on these kind of successive eruptions from the same active regions. Yes. Yeah, because eruptions happens, yeah, usually. So for long, we need a long cadence or the long time interval event, starting from many hours.
Yeah.
Then we can see that how the eruption is going on. Because first we need to store the energy. Then when that certain energy is stored in that exhibition, then we have the eruption. So it takes some time to then store the energy. It takes 4 and 5 hours, and then we need. So these kind of eruptions, some of the papers are there. Eruptions are always from the sun during its maximum activity phase, but still from the same active region. There are very few. So yeah, it's like this.
Cool. Navin, I want to thank you so much for sharing your paper with us today. It's a really lovely piece of work, and I look forward to seeing more of your papers in the future.
Okay, thank you very much. Thank you very much.
All right, everyone, thank you, and we will see you on the next one. Bye-bye.
Okay, thank you very much. Bye.